frequency, uh, an underutilized frequency division multiplexing, division multiplexing when it comes to circuit switching. Okay, but for the time division multiplexing, if you notice, we've kind of sliced it based on time. So when you allocate it, then this usually applies to calls, phone calls or whatever, because we know that phone calls cannot exist forever. You can't make a phone call forever. You can yami off for 2 years license. You can't. It just doesn't make sense. So ideally, it's better to allocate time slots instead. So whenever you need to make the call, then you use that given time slot allocated for you within the given spectrum, within given frequency spectrum, to handle that call. And once that time slot expires, a different a group of users can be reallocated uh, to use the spectrum as well. Okay, so in this sense, the spectrum is not allocated for a given user for unlimited time. So in a nutshell, with the time division, frequencies are not allocated to users indefinitely or for an unlimited time, but it's usually allocated based on time point or time division. Okay, for a specific time duration. Okay, so once that time expires, then that's it. Then a different sets of users can still access the frequency. So in this sense, you're actually managing the frequency spectrum much more efficiently. Okay, because nobody has it for the indefinitely, basically for a limited time. Nobody has for a limited time. You only have it for a given time slot or a given time period. Okay. So within these two, obviously, time division multiplexing is much efficient when it comes to management of our frequency spectrum that we have. Okay. Now there are the applications when it comes to application wise, uh, it depends. Okay. So like for instance, radio stations, for instance, or TV stations. You can't put TV stations or radio stations and a time division multiplexing. It wouldn't work very well if you think about it. So it means that when Joy FM or Radio Go comes online for say 5 minute time allocation, then they go off for a different station to come off and also take out that particular frequency. It wouldn't work out very well. So for application wise, certain application requires the frequency division multiplexing, while other application requires the time division, like calls, for instance, perfectly appropriate to put it in the time division, whereas services that relates to broadcast services and frequency division multiplexing is the most reliable way or the best option to go for. So we do have some calculations that we want to be looking at when it comes to some of these frequency when it comes to some of these frequency division multiplexing and time division multiplexing. So here's the question over here, which says assume that a voice channel occupies a bandwidth of 4 kilohertz. We need to combine three voice channels into one link with a bandwidth of 12 kilohertz, which is from 20 to 32 kilohertz. Show the configuration using the frequency domain and assume that there are no guard bands. Now, guard bands over here actually represent more or less like a leeway to prevent overlaps of signals of frequency allocation. So when your a system or a transmission is allocated a given frequency spectrum, there's a guard band that is put in place to before the next frequency allocation can take effect. And that gap is what we term as the guard band. Generally, they are designed to prevent uh, interferences between two uh, frequency allocated between two transmissions or between two users or two services. Okay, like for instance, some of the radio stations, if you notice their channels, one the channel after a given channel has got some gaps in between them. So if you take Joy FM 99.9, the next one will probably not be probably be 100 something. And so you do have some, there's always some gap, either at 101 point something. So there's that gap between the 99.9 to the 101 will form the guard band. Because they're designed to avoid interference between two uh, frequency channels allocated to a given transmission. Okay, so to solve this problem, we have to shift, well, solution-wise, we need to shift or modulate each of the three voice channels into a different bandwidth as shown. We're going to show a figure. We'll show, okay, so in this case, solution-wise, we need to shift or modulate each of the three voice channels to a, so let me see the diagram. Yes, in this diagram, we need to shift um, or modulate each of the voice channels to a different bandwidth. Okay, and we will use the 20 to 24 kilohertz bandwidth for first channel, and the second 24 to 28 kilohertz. Since the reason why we kind of separated between the what you call it, between the 20 to 32 kilohertz is to address our link channel bandwidth, which is 12 kilohertz. If we split them to that point, we have to look at that. We have to fuse this 12 kilohertz into each one to help us move on to the subsequent kilohertz. So each one of these voice channels of 4 kilograms can have their respective frequency allocation. So we do have the use of 20 to 24 kilohertz bandwidth for the first channel. The second channel will be from 24 to 28. So there are 444. So we can accommodate the 12 kilohertz bandwidth that we have. You know, it's 12 because it's 20 to 32. You have 12 kilohertz, which is 20 to 32 is 12. All right. And we need to, if you want to gain the 4 kilohertz out of this, then how many kilohertz of bandwidth can you fit within the 12? So there's going to be about 3 of them, right? That's 4 times 3 is 12. There you go. So that's what we have. The first one having from 20 to 24. That's the first one. And you have 24 to 28, and obviously 28 to 32. That'll help us achieve the our 4 kilohertz bandwidth occupations. Okay, so 4, 4, 4. That makes up a 12. Okay. So in diagram wise, this is what it will look like. So we're modulating the 4, kilohertz that's been assigned to these 3 devices. We need to modulate it for the transmission over a bandwidth link from 20 kilohertz to 32 kilohertz. So here's where the modulation comes in. So you notice that the first one takes 2024, second one takes 2428, and the third one takes 28 to 32. So all added together, you have your 12 kilohertz intervals that's been modulated together and transmitted over this bandwidth. And all the way. And when it gets to the receiving end devices, there's a bandpass filter that's able to reorganize the messages into their respective destination nodes. Okay, so the bypass filters handles the reorganization of the message and as well as splitting them into their respective destination devices and devices. So with this one we had there were no band guard. Now let's go to an example that uses guard bands. Here we do have five channels, each with 100 kilohertz bandwidth, and they have been multiplexed together. The question here is, what is the minimum bandwidth of the link if there is a need for a guard band of 10 kilohertz between the channels to prevent interference? So as I was mentioning, guard bands are designed to avoid or prevent interference. So now in this question here, we're looking at five channels, each having 100 kilohertz bandwidth. So if we were to introduce a 10 kilohertz guard band in between them, the question is how many is needed, right? Or what is the minimum bandwidth of the link if there is a need for a guard band of 10 kilohertz between the channels? So we're looking at the total bandwidth that's going to be occupied then. What's the minimum? That's what the question is asking for. What's the minimum bandwidth required to address these five channels of 100 kilohertz with 10 kilohertz guard band? So you can do the math. If so, 5 times 100 will be 500, and I'm going to add that to the number of guard bands that we need. In this case, you can say 5 times 10 to get the number of guard bands needed. If you put them in arrangement, it will actually be 4 guard bands that you need of 10 kilohertz. Because diagram, okay, let's look at the diagram solution wise so we can see that much more clearly. Yes, I'm looking at it, just looking at it, I can just tell if you have 5 channels, each one having 500 kilohertz, the bandwidth they're going to require is obviously 500 kilohertz. But the question is, how many guard bands bandwidths needed to add to this to form the minimal bandwidth required for all 5 channels? So yeah, there's going to be 4 kilohertz of guard bands. So the answer will be 500 plus 4 times 10 kilohertz, which is 40 plus 500, and I will give you 540 kilohertz will be the minimum bandwidth of the link required. Okay, so solution wise, that's exactly what I was trying to point across. Let's put across. Yes, so obviously 5 channels with 100 kilohertz will have 5 times 100. By the number of guard bands, it will be just because these are the 5 100 kilohertz channels, and we're introducing 10 kilohertz of guard bands, so more or less gaps in between them. You're only going to have 4 gaps: 1, 2, 3, 4. You're going to have 5. So in a way, you can say that whenever you allocated a number of channels with specific bandwidth, if you were to introduce guard bands, the guard bands will always be 1 less than the number of channels that's required. So when it comes to minimum bandwidth required for that number of channels to actually accommodate the transmission, you just have to consider the guard band to be one less than the number of channels required. I hope we got that clear. So that's how we got the 540 kilohertz. And like I said, application wise, radios and TV stations uses up some of these in a lot to address some of the frequency or time division multiplexing needs. So AM stations or radio stations, the guard bands that operate within that. FM stations as well. And then TV stations as well. And finally, we have mobile services, ARM services. I think it's advanced mobile packet switching also, which is the early mobile services, mobile phone services or transmission. So ARM service also use some of these today. Even though some of the frequency and time division multiplexing are being adapted within systems, I think most of the frequency allocation for mobile services revolves more or less within the time division, so we can utilize the frequency much more efficiently. Okay, so when it comes to the ARM parts, current mobile services or mobile technologies adapt the time division a lot as compared to the frequency. Okay, so that covers the application part. What about synchronization of time division multiplexing? For synchronization, we do have what you call a synchronous time division multiplexing, where the data rate of the link is it's usually the key factor in its design, and unit durations also plays a key role. So we do have a diagram over here that looks at how synchronous time divisions are used to carry information when it comes to multiplexing. The order in which these frequencies are grouped and multiplex as far as time is concerned, to make sure we synchronize messages in terms of frame messages efficiently, effectively. That's why we say in synchronous time division multiplexing, the data rate of the link is n times faster and the unit duration is usually much shorter, or it's n times shorter. So in that sense, you say, so it says n times faster, n times the number of times that the synchronous information data rate takes is much faster, but the duration wise is much shorter. So we do have all these messages that are coming through the multiplexed, so we can create a much faster time but shorter duration for the message delivery. A very, very interesting concept. Okay. And it seems like it's a bit confusing as well, especially when it comes to the multiplexing within the synchronous, because synchronous here means if you're more or less dealing with live transmission, the question is how do you keep them simultaneously or synchronously running within a time division multiplexing? That's the biggest question. How do you handle that? And that can be very tricky in terms of its application or its implementation. So let's use an example and illustration to help look at some of these synchronous time division multiplexing and its data rate uh, uh, illustration, or its data rate implementation or concept. So we do a figure. So from this right here, from based on the question of this diagram here, and he's saying that question is in the previous figure, the data rate for each input connection is 1 kilobit per second. Now, if 1 bit at a time is multiplexed, so a unit is just 1 bit, what is the duration of A, each input slot, and B, each output slot, as well as and C, each frame? So the question, how do you answer that question? So we can answer this question by saying that if we do have uh, a data rate owning up to 1 kilobit per second, we want to determine some of the various uh, input slots time durations or data rates when it's been multiplexed. Then for A, each input slot, the data rate of each input connection, which happens to be 1 kilobit per second, would mean that the bit duration is actually 1 divided by 8,000 seconds or 1 millisecond, because it's 1 kilobit per second, and since it's 1 bit that's been multiplexed, then for each input it will be 1 divided by the uh, the 1 to 1, it can be 1 divided by the 1,000 kilobits per second that's been allocated for that connection input or for that connection data rate. So in other words, 1 millisecond is the duration for each of the bits that you'd have. That would answer the first question. The second question, which is about the duration of the output slots. So let me see. Oh, exactly. So you have the data rate of each input connection is 1 kilobits per second. Yes. So that's what was mentioned. So for a single bit, it'll be 1 divided by that 1 kilobit per second, which is 1,000 kilobits, which is more or less 1,000 seconds, right? Because it's kilobits per second. So that's 1,000 seconds. So you have 1 divided by 1,000 seconds will give you the 1 millisecond. So that will represent the duration of the input time slot for just 1 millisecond. Sorry, millisecond. And that would apply to all the other bits as well, if you to have a sequence of them. The second question was each output slot, which is the duration of each output slot, would be looking at the, let me see, 1/3 of the input time slot, which means the duration is of the output time of 1/3 millisecond. Let me see. So we do have Okay, yes, exactly. So this is 1/3. The question is asked for each output slot. And since we have three consideration, we have the input slot, the output slot, and then the frame itself. They are going to take a sequence of bits. So each one will have uh, its allocation. And so in that sense, we have to split up into three parts, which is where we have the 1 divided by 3. So 1 divided by 3 milliseconds will be the time slot allocated for each of the outputs because it's dealing with both the inputs, the output, and then the frame itself. So the duration of each output time slot is 1/3 of the input time slots, meaning that the duration of your output time slot is 1/3 of a millisecond. And the last one is asking for the frame. Since there are three, you have the input, the output, and each frame, and it's going to be 3 times the 3 milliseconds that we needed, the 1/3 milliseconds that each output takes, which just took 4 back to the 1 milliseconds, right? Because you can have 3 times 1/3 per millisecond. Yeah, that would come back to 1 millisecond again because the threes would cancel out. So each frame carries 3 output time slots, right? Because it has the input, output, and then the frame itself. And obviously that means the duration will be 3 times the output time slots, which is the 1/3 millisecond. So when you do the multiplication, you'd have 1 millisecond as the duration that a frame will actually take in terms of duration. To basically service a single input unit. Moving on to more examples, or another example. In this case, we have this figure here, and we want to show synchronous time division multiplexing with a data stream for each input and one data stream for the output. The unit of data is 1 bit. The question you need to find is find the input bit duration, 1. 2. Find the output bit duration. 3. Find the output rate. And 4. Find the output frame rate. So how do you go about this question? Well, in a way, this will be the arrangement if they can be getting multiplexed. So we take, they all have 1 megabit per second. The first one has got all 111s, has got all zeros. This one has got 10101, and the last one's got 00100. And if we are multiplexing it together, the frame that would have in terms of first in, first out, or last in, first out, then in that case we would have so let's say we're using last in, first out. In that case, the last bit of the first bit, so we're going to so if we're going with first in, first out in terms of arrangement for these 4 messages, then we can say that if we're to go with the last message first, then we can just go with 0101 and then 0001, 1101, 0001, and then 0101. So that's the frame going on. So you have the 0, 1, 0,